Today we're going to do section chapter 7.4. First, let's scan the book. This I think this is a fairly long chapter, so it might take a while to get through, but doesn't make any difference. Okay, and a little bit closer. Okay, and then a little bit closer on the bottom. All right. Next, page 234 and 235. Okay, let's see. Is that clear enough? Well, whatever. We'll zoom in a little bit closer on top. Okay, and then a bit closer on the bottom. All right. Next, page 236 and 237. Let's see. Here we go. Okay, and then a bit closer on the top. And then on the bottom. All right. And then 238 and 239. Okay, a bit closer on the top. And then closer on the bottom. Okay, that should do it. So let's start on page 232. First, please read the introductory paragraph yourself on the top of the page, and I'll begin talking right down here, the definition of a surface integral. Now, what we're going to talk about is similar to what we did with the line integral, in that we're going to start with some kind of a surface, and we'll call it sigma, capital sigma, and which is normally used for summation, but right now we're going to use it to mean a surface. Okay, so here's some surface, but let this be a finite piece. That is, it doesn't extend to any direction into infinity. So finite means well bounded. So then a subdivision is that, so you cut it into parts, okay, with a bunch of borders. The borders are closed curves. We call them CK, which are inside sigma, and then it divides it into n subregions of each have a small amount of area, delta sigma k, and then so that's okay. Now I have a picture here to show you. Here's a sample sigma that, as you, okay, that is that good enough? Somewhat, you can kind of see it, okay. So sigma is some surface, and we divide it. In my case, I just divide it in with squares. Okay, so imagine each square is a CK, the curve around it. And each one has, of course, the CKs on common boundaries, then the CKs repeat themselves. But anyway, we have a bunch of CKs going, which are squares, right? That the boundary of the squares that divide the surface sigma into a bunch of small ones. All right. So next, let's continue reading. And then the next sentence is that. And each little subregion has an area. We'll call the area delta sigma k, okay, for each k that represents the little subdivision, that little piece of the subdivision. So then the diameter of the region, of this region, is the length of the longest line segment, means straight line, okay, whose end lies into this region. Now, because due to the curvature of sigma, then the line segment might not completely be included in the lie inside sigma itself, but that's okay. We're only measuring the distance. We don't care if the middle of the line isn't included. As for example, I have drawn a diameter here. As you can see, the diameter of that square is, well, the longest distance will be the diagonal, but you notice that most of the, none of the diagonals included in sigma itself except for the endpoints, okay? Because sigma dips down at that point. So, or if it comes up, like the other example, that is, I draw in dotted line because it's under the curve. So, yeah, it's, well, anyway, so, well, either way, okay, whether it's up or down, the point is it doesn't, the diameter, part of the diameter doesn't need to be covered. We don't really care. We just need to know how long it is from, what is the widest point from one end to the other. So then we have, so as the book says, since sigma may be curved, the intermediate points of the segment need not lie on sigma. So then the norm, which is the triangle, okay, delta, which is denoted by the absolute value of delta, is the largest of the diameters of all the subdivisions. And then, so eventually you can imagine we're going to force the triangle into 0, okay, as we increase the subdivisions, and so to make them each one smaller and smaller. Now, let's consider there's some function called P(x,y,z), which is a three-dimensional function. Is defined for every point in the region that we care about. So P(x,y,z) is some function that is defined at every point of sigma. And then there's a specific point, psi k, eta k, that was called, the last symbol I think is pronounced zeta. I'll figure out later. And let's psi k, eta k, and zeta k be a point on sigma that is, and it can be either on the inside of the little subdivision or on its boundary. It doesn't matter, okay? And well, it's somewhere in there. Then the surface integral will be defined as the limit as the biggest triangle diameter forced to 0 of the function at some point inside the little subdivision times the area of the subdivision. And together it will, if this limit exists, okay, as you force everything go to 0, if the limit exists, then this will be called the surface integral. And now if the sigma happens to be a flat thing on the xy plane, then this is the same as the regular double integral. And as a result, the double integral is a special case of the surface integral. The double integral is just integrating on the xy, some surface on that's flat and, yeah, on the xy plane. Now, next let's consider the moment of inertia of some piece of surface in space. And let's say you have a piece of metal or something, okay, that is some sheet that is sitting in space like that, and its density is given by, yeah, see that thing sitting in space, okay? Let's say its density is given by some formula called sigma xyz. And so then if to calculate the moment of inertia, we can just pull out the old formula, which basically means the moment of inertia is the distance from the axis that you're spinning it on, which is, as an example, then we can, if you're spinning it around the x-axis, then the moment of inertia will be calculated using this formula right here, which is y squared plus z squared. That's the r squared, that is the distance, radial distance from the x-axis, times the density, okay? Then we integrate as the d sigma over the sigma surface. And that should, and by the time you get out of all that integration, then you will get the moment of inertia of your surface. Now, to actually calculate it, of course, we are not going to take the limit or cut anything into any pieces. We're going to try to reduce it into a regular integral, that is a double integral. So to do that, let's consider how we're going to pull this off, okay? And to do that, we'll make sigma a simpler surface that doesn't have too many wiggles. So let sigma defined by, in this case, defined by a function that's z equals to fxy, which means means that sigma is has only one, z has only one value. It doesn't double itself back. Put it another way is that sigma is cut in a single point by a line parallel to the z-axis and has the projection r in the xy plane. I have a picture of that in this case. Okay, we have a surface on top, which is sigma. Okay, and that it behaves in such a way that if you draw any vertical line straight up, it'll only go through sigma at one point. That is, the thing doesn't fold itself back, so that it cuts it in 2 points. Okay, so it's a regular function, z equals fxy, and also it projects a shadow on the ground. In my case, I just cut this thing into a rectangle. Well, this is not a rectangle, but I cut it in such a way that its shadow is a rectangle. Just keep things simple. But remember, the shadow could be anything. Right? I mean, we're just making a point here. So we have a piece of this thing that it doesn't double back, and doesn't do this, and then it has a shadow, and okay, so far so good. And next we have let's see. So next we're going to build a subdivision on it. And we're going to cut it into slices, okay, which is what I have done here. Notice this part where things are being cut. And I sliced it into in such a way that its shadow is also a subdivision, and they go by the same name. So the delta is the subdivision on top, and its shadow, also called delta, is the subdivision on the bottom. Okay, and then specifically you can see one of the little subdivisions where the point is called psi k, eta k, and zeta k, which is that's the point on the surface, and that point is the same as on the bottom, that on the ground, that is on the xy axis, the point is just psi k, eta k, okay, with zeta k equal to 0, and specifically it is equal to, and the last coordinate zeta k is the same as function f of psi k and eta k, because the surface is defined by c equals to f x y. Okay, so delta zeta k is the area of the little subregion. Okay, so that looks tolerable. So let's continue. Now, if for some reason we can figure out how to describe that little area on top in some way as some kind of a function of the little area on the bottom, then we have a way to calculate things. That is, see, this is the little area on top, is that little rectangle there. Okay, it has a corresponding orange rectangle on the bottom. If we can somehow figure out what their relationship is, say this thing multiplied by some number is going to be equal to that, then what we can do is this part. Then the sum takes a form of this. That is, we can then use the delta sigma k can be calculated as a delta s, like definition 3, chapter 6, which is, let me find it. No, that's not it. Definition 3, chapter 6. This is it. Okay, so we're going to have the integral that looks like this, because everything looks similar except that the delta sk will replace delta sk times something, okay, or have some relationship that turn delta sk into delta sigma k, and then we can turn that surface integral into the double integral and then calculate it. So that is the plan. But first we have to all right. Anyway, so next, let's continue with Theorem 7 on the following page. So now we're on page 233. So next, let's consider Theorem 7 on page 233. We have a function pxyz that is continuous in a volume. Okay, so p is a function that is defined in the 3D object. Every point inside the object, the function has a value for it. Next, sigma is the surface over some region R, like I showed before. Okay, this is and then the f, z equals to fxy is a function that's inside the region R that is on the ground, and sigma is on top. Okay, R is on the ground, and fxy is a function that's on top, but its domain is in R. All right, and then next sigma lies in the volume that we talked about earlier, assuming there is a finite volume. And so then in that case, then the double integral of sigma of p d over sigma of p d sigma does exist. The double integral is defined as what we mentioned earlier. Okay, that is, this thing as the limit of this will exist, and furthermore, it equals to this specific formula right here. Okay, that it not just exists, but we can calculate it this way. That is, we can calculate it by substituting z as fxy, because z equals to fxy in on the surface. Okay, so we're substituting there, and then plug this thing in. This f1 and f2 comes from z equals to fxy here, and then we integrate it like a regular surface, like a regular double integral. So that is the formula. Now to prove it, then, first I should mention that the theorem enables us to reduce a surface integral, which is going all over the space, into an ordinary double integral, which just is the one that we're used to doing, okay, on the ground, so to speak. So then, to prove it, first we will consider equation 17.1 of chapter 6. Which is on page 202 of the book, okay, which is this thing right here, okay. This is page 202, and let me wait for the formula camera to, yeah, here, there's 202, but, and look at this formula right here, which states that if you have an area on top, okay, that's defined by some function z equal to fxy, then the area in a small in the region, whatever it might be, is given by this formula right here. Okay, the square root of f1 f2 all squared square root ds, and that's what we're going to plug it in right here into the delta sigma formula. And in the same way, since delta sigma is the little area on top, and then it equals to the ds. Plug in the exact same formula, because we have the same situation here. So the little small delta zk would be equal to this thing of ds over the little region rk. So you can, yeah, this is where is that a k there? Yeah, I think so. So following that exact formula, right? And that and maybe I should show you that picture again. I think I'll do. As see, we have let's see, this part here, we have that delta sigma k on top, okay, is the little square shaped thing here is exactly the shadow of, is the function value of the thing on the bottom. And so according to the formula, we can apply this this formula right here in order to let's see, where's this formula, which applies to a similar situation. See, there's even a graph for it. See, what's on the top, you can calculate it by what's on the bottom times that square root thing. All right. So now that we know that, we will look at this. Okay, so once we know that, then the next step is we're going to yank this out. We're going to yank this thing right out, okay, into this. So yank it out by the MVT, okay, law of the mean, which just means that you can pull out what's inside the integral and then multiply it by the integral without it, and so that equals delta sk. Where a and b are at some point inside our region. So once we have this thing, we plug it into equation 1 on this side, okay, delta sigma k put it in right here. So then we'll have different variables here, variables, a bit of a different variables maybe, but that doesn't matter because there's the handy dandy Duhamel's theorem, which says that everything will work out if you do that, which is Duhamel's theorem on page 198, which, yeah, see, and the Duhamel's theorem here has just 2 variables, but that's good enough. Okay, we just doesn't matter if the variables are different, even if it has 2, 3. In any case, it all works out. Okay, we can reduce it into the double integral, and with that, that is the end of this proof. Now, this Theorem 7 is we can modify, of course. Theorem 7 we have set up as z equals to fxy, but we can totally use it. It doesn't have to be. It can be x equal to fyz, you know, just looking at it from a different angle, or y equals to fxz, that all works out. And furthermore, if sigma can be decomposed into a finite number of parts, each of which is cut only once by a line parallel to some axis and has a continuously turning tangent plane. That is, if the whole sigma is twisting all over the place, but we can cut it into bits where each bit fits the Theorem 7 hypothesis, then we can still apply the theorem and just add the whole thing up. Right? Because we are doing integration. And another point we should mention is that radical sign, you know, the 1 plus whatever, this thing is also secant gamma in the z direction. In the other directions, it might be secant alpha or secant beta. Okay, so in the z direction is secant. This radical is secant gamma, where gamma is the acute angle between the normal to sigma and the z axis. That is also mentioned before on the page 202 and 203. Okay, and actually 203 especially. See, the cosine gamma is this thing right here. So secant gamma is the denominator, in other words. And we already did this back in the day. Okay, so that is just to refresh your memory. And that is that for Theorem 7. Now, to show how we can possibly have modify this theorem so that we use x equal to fyz instead. Okay, that is, we're going to work things in that direction. But everything else worked exactly the same way. Let's look at example A, where we're made to do this. So in example A, we're computing xyz over some sigma, and sigma is the surface of some tetrahedron. Now, to calculate this, well, you just go ahead and follow the Theorem 7 exactly. Okay, but first draw out the tetrahedron might help. We have the tetrahedron it looks something like that, and so we're going to integrate. The book wants us to integrate by casting. We have the tetrahedron has 4 surfaces, but being that we're integrating x, y, z. And then the surfaces on the coordinate planes automatically have integral value 0 because of the x, y, z business. So we only have to integrate 2 surfaces where this depicted in the book and here as sigma 1 and sigma 2. Okay, those are the 2 that will give some value. Now to integrate that, then we follow the rules, okay, and plug it in. Where we're integrating from x and z only. So then we plug y, express y in terms of x and z, and then plug it in here, and then do that radical thing, okay? Where function f is defined as a function of x and z, and plugging everything in just like Theorem 7 says, okay? So the function now is, instead of xy, is xz, but that changes nothing. We take the first and second partial derivative, square it, take square root, etc., add 1, and come up with some value. And then that will give us this thing right here. And so that's what I did. I wrote down the formula. I have this integration out, okay? The stuff in the radical sign happens to be constants because these are just regular planes, so they have the derivatives are constants. And so then the first radical gave me that value, and then the second surface works similarly. It gave me a different value. They both happen to project to the same surface, okay, this gray area here, which is the Rx. And we integrate in that area and so on, come up with these values, and then yeah, and that is that's that. And by the way, this problem is also used in the homework in homework problem 3. So I will show it to you right now in case I forget to do so later, or don't want to bother. Okay, so that is and that's some information for homework problem 3 if you need to look it up later. Okay, so that's example A. Please do this yourself. Okay, make sure that you understand how it's done by not looking at anything that I just told you, but rather just sit down and do this like some kind of homework, which is very nice because you know that if you run into any trouble, there's the book explanation, there's also my explanation. You know, you can't go wrong, so to speak. And then next thing I want to talk about is example B. Okay, let me look at it first. So next, let's look at example B. We're calculating the double integral of x squared c cosine gamma d sigma. Sigma is now the unit sphere, and gamma is the angle between the exterior normal to the sphere and the positive z-axis. Okay, now the problem with this is the two hemispheres. So for the unit sphere, we'll consider two hemispheres, the top one and the bottom one, like we normally do, which is fine, except that both of them have the problem of not belonging to C1 on the unit circle because they take a dive, okay, on the edges. So what we're going to do is cut out the edges, okay, as it says here, by we cut out the equator by the cylinder x squared plus y squared equals to 1 minus sigma squared. And so we'll use this cylinder here, okay, to cut out just the equator, or the, plus a little bit around it. Okay. So now our surfaces are reasonable, and then we'll take a limit as epsilon goes to 0. So and with that trick, then we can apply Theorem 7 that we just learned to calculate the surface integral of what we're looking for here. So to do that, let's calculate some of the details. Okay, we need to calculate this specifically. The radical here, the 1 plus f1 squared and f2 squared. So after some cranking of calculations, you will figure out what z is plus or minus the square root of something, right? Then we figure out what f1 is, f2 is, and then plug it all in, and then eventually you realize 1 over z is secant gamma, which means cosine gamma equals to z. Or secant gamma equals to 1 over z. And sometimes we might need to stick the absolute value on there to take care of things like whether it's pointing up and down, being that it's an external normal. It's a bit of a detail. Please think about that yourself, okay? And eventually you'll come to terms with it. So anyway, the point is that the cosine gamma is going to be equal to z. Now, and then so let's do the calculations. Plugging everything in, okay, we have the top, which equals to this thing right here, when cosine gamma is also z, and d sigma has also has that thing in it. So, but anyway, so we eventually notice that the integral is going to be this thing, and that's the top, plus this thing, which is the bottom. The reason is because on the lower hemisphere, we have two negatives here. We have first, the secant gamma, cosine gamma is less than 0. And secondly, the z itself, the surface is also negative. So two negatives makes a positive. So that's why it ends up being a plus here already. Anyway, so that we are doing the integrals simply by calculating double of the top is good enough. Okay, and then so when we substitute everything into the polar coordinates, and make sure we don't forget the r. Let's see, the RDR. Okay, remember to convert to polar coordinates, you have an RDR, not just DR. And so please don't forget that, like I did. And so once you do that, then you come up with the the proper answer. Yes, I also have written down some stuff here for your reference. Example B. This is example B, not A. Okay, we already did example A. So let me see. Yeah, notice that secant gamma in this case is 1 over z. So then the cosine gamma and secant gamma cancel themselves out somewhat, and which is how we came up with this equation. Okay, which yeah, so that is, anyway, I think that makes enough sense. Okay, so we will move on. So next, let's look at page 235, where we consider theorem 8. So let's have P, Q, and R as C1 functions of in the volume V. Okay, and then V is bounded by sigma star. Now, did I wait a second? I think I haven't mentioned the part before. Yeah, section 4.2 is where I should have started. Sorry. Now let's go back to a little bit on the previous page and look at section 4.2. There are some comments that we can't miss. Now a surface sigma is denoted as sigma star if its boundary of a three-dimensional region V, okay, and then it is a region Vxy, Vyz, and Vzx. Now what that means is that Vxy, for example, is a function such that it has a bottom region R where it projects to, okay, and it goes from phi to psi. That is, it does that thing. Now, but this has to not just be Vxy, but somehow be Vyz and Vxz as well. So that there's a way to write this volume in all three ways, in all three dimensions. Now that such a function, such a sigma star would be, unusual. The first example you can think of is, of course, a cube like this. Then it would be a sigma star, right? But something more than a cube, can something more than a cube be sigma star? Then another possibility is this thing right here in the picture. This is actually the illustration of example A over here. I didn't know that the illustration is clear over here, so I drew one myself. But anyway, this is also a sigma star. That is, you can depict this thing in Vxy, Yz, and Zx. All three is possible to depict it with all three directions. All right. So then. And in this situation, phi and psi has to be C1. Okay, so it's not just Vxy has to be presented this way, but phi and psi require to be C1, and such that the sigma star has a continuously turning tangent plane over the parts of the surface that has these defining functions. So it can have corners, right? And it might have corners like this one, but at least on each plane then is a continuously turning tangent plane that in order to be C1. All right, so having said that, now let's go to theorem 8 on the following page, where what did I say again? It doesn't matter. So P, Q, and R are C1 functions in a volume V. V is bounded by sigma star. Now, and alpha, beta, gamma are the directional cosines, or the directional angles of the exterior normal of sigma star. All right, so let's worry about that in a little bit. So now, so what does the theorem say? The theorem says the integral, the triple integral over V of P1, Q2, and R3 dV is going to be the double integral over sigma star, of P cosine alpha, Q cosine beta, and R cosine gamma of d sigma. Okay, remember the alpha, beta, gamma are the directional cosines, so to speak. And as a result, they put the cosines here. That is, they're the angles, and cosine alpha then is the angle of the normal with the angle makes with the x-axis, and cosine beta is the angle of the normal make with the y-axis, and then cosine gamma is the angle with the z-axis. All right, so if V is defined, say, by equation 2, let's say V is defined like this. We're now reading the proof. Okay, so V is defined like this. That is that is Vxy is constructed by some kind of region on the bottom and it goes up from phi to psi. Okay, so then by Theorem 5, Chapter 6, the triple integral of V can be expressed as the iterated integral of double integral over R and times the integral from phi to psi. Now that is on page 207, and I want to show it to you right now. That's the iterated integral for the double integral, Theorem 5 right here. Okay, so f is continuous. So we have Vxy, which it goes down from phi up to psi. So then the triple integral is equal to the double integral over R going from phi to psi of x f x y z. All right, so then to refresh your memory of that thing, okay? It's been a while since we did that. But anyway, we have, so we have that come out. And so the next step is, if that is the case, to evaluate it, then we just plugged, because this is R3, okay? We're taking, that's why it says R3, that matters. Right now we're proving that this equals to this. That is, these parts are correspondingly the same. That is, P1 will be equal to this integral, the triple integral of P1 equals to this part. Triple integral of Q2 will be equal to the double integral of this part. And right now we're proving this equal to this part equal to this part. Okay, so then we have that, and that by definition of the double integral means the top, okay, minus the bottom. So far so good, and then the next step we have phi and psi, and let's see. So next step we have the ds. Okay, each ds here is replaced by cosine gamma d sigma. That's because of the previous theorem where ds is equal to the secant, ds times the secant is d sigma. Okay, as see the right from theorem 7. So then if we have d sigma would be, so that's why as a result this is the secant. Yeah, this is secant, the square root thing with 1 plus f2 squared and 1 squared and f2 squared. That is secant gamma. So secant gamma times ds is equal to d sigma, or put it another way, d sigma times cosine gamma is equal to ds. All right, so that is that's how we got to here. Okay, so d sigma times cosine will be equal to the ds. So we got to this part. Now now pay careful attention to what we're doing. We have the first integral is over phi. Phi is the top one, okay, which we call it sigma 1. That stands for phi. And is that phi or psi? Now I'm forgetting what these symbols are called. Doesn't matter. Let's call the top one psi and the bottom one phi. Okay, this is the bottom symbol, and that's phi. That we'll call it sigma 2, and the top one I'll call it psi, and this will be called sigma 1, the surface. So we're integrating over the top one, which becomes this one, and then sigma 1 is the upper one. Okay, sigma 2 is the lower one. The word nap, we will just the book used the word nap. We'll take that to mean surface. So then we have, and bear in mind that cosine gamma is bigger than 0 because it points up on sigma 1. We're talking about the outward normal here. So the cosine gamma has to point up on sigma 1 and point down on is negative on sigma 2. As well, the negative positive, is think about it and it will make sense. So then we have now the next thing is, if it were true that phi equals the psi on the boundary of R, okay, the thing is just stuck together like a pancake or something, then the whole volume will be equal to, then there's nothing else to worry about. Then we have there is no other surfaces. We have and because one is positive and one is negative or something, then the triple integral is indeed equals to what we're setting out the proof, because of the sign. So one is positive and one is negative. Then the double integral over the whole surface will be equal to this thing, and that is of course the original triple integral. But that's if the two surfaces sigma 1 and sigma 2 are stuck together on the boundary. But what if they're not stuck together on the boundary? Then there will be a cylindrical surface, okay, around it. There's a wall, there's a top surface and bottom surface are not stuck together. There's a distance between them. So there's a wall that is a cylinder. Now, along the cylinder, however, the cosine gamma is 0 on the cylinder. That's because gamma on that surface, you remember gamma is on the vertical surface, it's going to point horizontally somehow. And if that does, then it makes angle pi over 2 with the z-axis. And so cosine gamma is pi over 2, that means cosine gamma is 0. And therefore, gamma is going to be everywhere 0 on the cylindrical surface, okay, right here. And that's very important. So we don't have to worry about it. Therefore, this equation stands even if the two boundaries, the two surfaces are not stuck together, that they are actually far apart. The cylindrical surface is always going to be 0. So then the formula works as equation 3 said. So far we have proven that the last part, the green part is equal to the green part. And then the other parts in almost identical parallel arguments are also equal to each other. And that's how we can prove Theorem 8. I will finish this section in the next video.